All right, let me let me come back to this. Okay, so with physics, with physics, we are looking at topical questions. So although we are using this model paper, okay, which the teachers in Sabah came up with, but we are looking at questions by topic, lah. Okay, so as we go from question to question, we will kind of like do revision on that topic. So the first topic that has been requested is the topic of waves, okay, which is chapter 4 from chapter 5 from 4, chapter 5 from 4. Okay. Um Hold on. Can you guys see the screen that I'm sharing? Can, right?
Can.
Okay, thanks. Okay, let me talk about the paper one paper first lah. Okay, I think a lot of some may not realize this as you answer the question. Okay, so I think it's good that I mentioned this lah. Now, in the exam, okay, in SPM lah, the paper is arranged. The questions in the paper are arranged in such a way that they go from chapter to chapter, which means okay, let's review lah. Let's review all the chapters there are. So Form 4, okay, chapter 1 is Introduction to Physics. Okay, chapter 2 is Force and Motion 1. Chapter 3 is Gravitation. Okay, chapter 4 is Heat. Chapter 5 is Waves. And chapter 6 is Light. Okay, and then in Form 5, so ugly. Okay, chapter 1 is Force and Motion 2. Chapter 2 is Pressure. Okay, chapter 3 is Electricity. Chapter 4 is Electromagnetism. Chapter 5 is Electronics. Okay, chapter 6 is Nuclear Physics. And chapter 7 is Quantum Physics. Okay, of course, chapter 6, chapter 7 will not come out in your trial exam because we haven't studied that yet. But what I want you to realize is that the paper 1 is, in our experience, as I've said, no one has actually seen the paper that you're about to sit for, and yours is the first batch of the new format. But if we follow the old format rules, and when I say old format, it's not just yang sebelum tahun ini tau, is sejak saya dari bangku sekolah lagi, memang begitulah itu diorang set kertas begitu. Since I was in school, the arrangement of the paper 1 questions always starts with Form 4 chapter 1 and ends with Form 5 chapter 7. That's how it is. So you need to know, okay, that when you need to know the entire picture of Form 4 and Form 5 so that you can get your brain or you can get your mind, okay, to think that, oh, okay, lepas bab ini, lepas bab ini, lepas bab ini, ini. Okay, one of the greatest struggles for any student sitting for paper 1 is they don't know which chapter that they are answering this question from. This is a great tragedy lah. Okay, because when you know all the chapters, okay, when you have a good idea of how the syllabus is structured, question number 1 is eating lah. Okay, definitely question number 1 will come from Introduction to Physics, and question number 40 is definitely from Quantum Physics. Okay, I cannot say that, okay, question 1 and 2 is from intro, question 3 and 4 is, no, I cannot say that. What I can say for certain is that after intro is force and motion 1. After force and motion 1 is gravitation. After gravitation is heat. After heat is waves, and so on and so forth. Okay, so when you realize that, then you kind of know that, okay, saya mau tahu ini, saya kena tahu, okay, bab ini about apa, bab ini about apa. So have that in mind whenever you're answering a paper 1 question. Because there is a certain structure to it. Bukan dia orang main campak saja semua soalan itu secara random tau. This is not quizzes. Okay, it's an exam question. Quizzes is random lah. The exam question, there is a certain structure to it. Paper 2 is a different story. Okay, paper 2 dia memang random, but paper 1 is very structured. First question, introduction. Last question, quantum. Definitely. Okay, and you see this over here lah. Question number 1 and number 2 is from Introduction to Physics. Okay, question number 3, you see a velocity time graph, you know that this is chapter 2. Okay, question number 4 is chapter 2. Question number 5 is also chapter 2. Question number 6, also chapter 2. Question number 7, this is gravitation already. Okay, because there's a force between the two. Okay, question number 8. This guy is, musing. Okay, the centripetal force lah. Centripetal force is chapter 3. Okay, so have this in mind when you're answering a paper 1 question, so that you know. Okay, don't just know all the physics facts, you also need to know the structure of your entire physics syllabus. So that you know, oh, ini dari bab mana ini ya? Macam saya tidak pernah. When you know that, that's half the battle lah. Okay, that's a small part of the battle. Okay, but since we know that waves, which is the topic we are going to look at today, waves is Form 4, Chapter 5. Okay, so it's going to come from somewhere over here lah. So it's going to come after heat. Okay, so heat is, okay, question number 12 is heat, okay, because it's a curve over here. And question number 13, okay, is where waves start coming in. Okay, so let's look at this. Displacement time graph, wave. Displacement time graphs tell us two important information. Number 1, they tell us the amplitude. Okay, they tell us the amplitude, and the definition for amplitude is the maximum displacement from the equilibrium position. MDFEP. Okay, maximum displacement from the equilibrium position. Remember this definition for amplitude. Okay, I can think of many acronyms for this MDFEP, but I'm not going to say it. Okay, MDF lah. So maximum displacement from the equilibrium position is the amplitude. Okay, the second information that the displacement time graph tells us is, and this is a very common, this is the period, because this is time. Okay, so the distance between the two crests, or the distance between the two troughs, or the distance from one point to another point in phase, okay, is the period. And the period, the definition for period is time taken for one complete oscillation. Okay, and emphasis on the word is complete. Okay, no complete, no mark. Okay, definition for period is time taken for one complete oscillation. Means pergi ke sana dan kembali. That is one complete oscillation. The time taken is called the period. And you know this period from the displacement time graph. Another type of graph that you should also know is the displacement. Okay, displacement against distance graph. Okay, displacement distance graph tells you the same thing. It tells you the amplitude. Okay, but the distance between the two crests or the two troughs is known as the wavelength. So you need to know which graph you're looking at. In this question, they are giving you a displacement time graph. So don't confuse the period and the wavelength. You cannot get the wavelength from the displacement time graph, because the x-axis is time, and you want to count length. How can you count length from time? So you can count length from a distance graph, but not from a time graph. The question is, what is the frequency of the wave? Okay, frequency is number of complete oscillations. Again, you see the word complete over here, which always students miss out for some reason or another. Okay, in 1 second. Okay, and the relationship between frequency and period is frequency equals to 1 over period lah. Period is t. So you need to know what is the period first. Okay, when you look at this one, the period is 4 seconds. Okay, so period is 4 seconds, 1 over 4. 1 over 4 is 0.25 hertz. Okay, so of course, I'm giving you all this extra information which has nothing to do with the question, but I want you to take note of this. Two graphs in the waves, displacement time, displacement period, displacement distance. Both of them give the same information, which is amplitude, but both of them give different information, where one is period and one is wavelength. Okay, and from the period, you can count the frequency. Okay, frequency is 1 over period, and the unit for frequency is hertz. Okay, or S minus 1, but we rarely, kita jarang pakai ni S minus 1 lah. Okay, we usually use hertz. Okay, H-E-R-T-Z. Okay, which diagram shows an example of a longitudinal wave? Okay, let's talk about the definition of longitudinal and transverse wave. Okay, waves got two types. One is transverse and one is longitudinal. Okay, transverse waves is direction of propagation. Sorry, direction of wave propagation is perpendicular. Okay, to direction of what? Vibration. Direction of vibration of particles. Hold on now. Sorry, senior moment. Direction of propagation is direction of vibration. Oh yeah. Okay, but direction of vibration. Okay, of particles. Manakala, okay, in longitudinal is direction of wave propagation. Okay, same line now, is parallel. The only fundamental difference is these two words only. To direction of vibration of particles. Okay, so one is perpendicular, one is parallel. Let's talk about wave propagation now. The common examples. Let's talk about examples first. Okay, examples of transverse wave. Okay, most common is Isabella. No, is water wave. Okay, water waves, light waves. Okay, these are very common transverse. Longitudinal only got one. Okay, which is sound waves. Okay, this is longitudinal. Now, what do we mean by direction of propagation? So for transverse waves, it will look like this. Okay, the wave is moving this way. Propagation dalam bahasa Melayu is perambatan, which also doesn't really make much sense sebab ini bukan bahasa biasa. But we don't say waves move. Okay, because actually waves are not moving, they're just transferring energy from one place to another place. So the transference of energy is what we call propagation. Okay, kita propagate the energy lah. Okay, so we always like to think that waves are moving. Actually, it's not. The waves are just staying where they are. Okay, because what is happening to the molecules, they are just going up and down as the wave is being propagated. They're going up and down. Okay, just like if all of you form a circle and you all start to hold hands, right? And one person moves his hand up, the next person has to move his hand up, and then it follows suit. So the wave is moving, propagating. You're transferring the energy to the next person. But are you moving? No, you're not. You're just going up and down. Okay, so very, very important. So the vibration of the particles is up and down, but the propagation is this way. But in sound waves, okay, the sound waves will look like this. Okay, where the molecule is going from left to right and the wave is still propagating this way. So dia punya arah sama. The sound waves are moving left, right, left, right, left, right, left, right, and the sound wave the particles are moving left, right, left, right, but the sound waves are just carrying forward. They're just propagating forward. So the direction is the same direction or parallel. Okay, then we call this a longitudinal wave. But in perpendicular wave, in a transverse wave, it is perpendicular. And we see this most often in water waves and sound waves. Kalau ada anything that you need to remember, if you don't remember the definition, remember the example. In paper 1, this is a very common question. Give an example of transverse wave, example of longitudinal waves. Okay, and since we're on this subject, I might as well talk about the longitudinal wave. Bahagian yang kempis-kempis ini, this part is called compression. Okay, dan yang lebar-lebar ini, this is called rarefaction. Okay, and for transverse waves, okay, the wavelength is the distance between two successive crests, yaitu sini dan sini, or two successive troughs. Okay, which is di bawah sini dan di bawah sini. But for longitudinal waves, the wavelength is the distance between two, sorry, I'm very lazy to write, successive compressions. Okay, or rarefactions. Okay, so for example, in this compression, this is the center. In this compression, this is the center. So this is the wavelength. Okay, or in this rarefaction, this is the center, and in this rarefaction, agak-agak lah. Okay, this is the center. So this is the wavelength. Okay, dua compression or dua rarefaction yang berturutan, successive. Okay, the word that is commonly missed out is the word successive. Okay, just like the one that I said just now, the word that is commonly missed out. Okay, successive, we need to be very careful with this. Okay, back to the question. So which shows an example of longitudinal wave? When you think of longitudinal wave, you need to think about sound waves. Okay, light cannot, it's transverse. Okay, water ripple, lagi cannot, also transverse. Okay, so that leaves us with C and D. Okay, spring is moved up and down. Dia macam water waves, so it's also transverse. Spring is pushed backwards and forwards. You push backwards and forwards, the wave moves. You will see the wave moving, but your spring is moving backwards and forwards. So this is the answer. This is longitudinal waves. Okay, example of longitudinal waves will be sound waves. All right, 15. Diagram 10 shows water waves change direction when they move from shallow to deep water. What is the name of this phenomena? Okay, shallow and deep water, we are talking about different densities. Okay, and when we talk about different densities, we are talking about refraction. Okay, refraction. Refraction is definition. The bending of waves, okay, when they pass through mediums with different densities. Okay, the waves look like they are bending lah. Okay, dirang kena bengkok, pembengkokkan gelombang. Okay, or the changing of the direction of the waves when they pass through mediums of different densities. Okay, so when we talk about refraction of waves, we need to think about the density of the material lah. In shallow water, okay, in shallow water, it is more dense. Okay, in deep water, it is less dense. Okay, same amount of water, different amount of space. So shallow water got less space, but you have the same amount of water, so it's more dense. Okay, in deep water, there is a lot of space for the water, so it's less dense in that sense. Okay, so pergerakan daripada more dense to less dense. No, this one is covered in light. Should I cover this? Okay, never mind. I'll cover this in light later. Okay, so as they change density, okay, what changes is the direction of the propagation changes. Now, a few things doesn't change. Okay, in refraction, okay, in refraction, there are a few things that no, actually only one thing doesn't change, which is the frequency. Okay, the frequency doesn't change. Okay, what changes, okay, is the wavelength and wave velocity. Okay, so in this one, the frequency doesn't change, but you see that the wavelength changes. Okay, shallow water, the wavelength is small. Deep water, the wavelength is big. And this makes sense to us. When you go into sea, right, as the water comes nearer to you, you find that the wavelength is very small. But in the deeper water, the wavelength is very big. You know, you're talking about like that, like that, like that. Okay, but in shallow water, as the waves come nearer to you, the waves will be like that. Okay, very small wavelength. But the frequency is still the same. Okay, this is a very the very difficult thing for us to imagine. The frequency of the waves is still the same, but the wavelength has changed, and also the velocity. Okay, V equals to F lambda. If the F doesn't change, okay, let's take a look at this. If the F doesn't change, when the wavelength decreases, the velocity also decreases. Okay, so that's why in shallow waters, when you stand at the beach, right, you find that generally the wave speed is a lot less. Okay, frequency is the same, the wave speed is less. So that's why you can swim very happily at the sea lah. Try going into deeper water. Okay, try going to deeper water. The wavelengths are very huge and the wave speed is very fast. Okay, because the wavelength is big, although the frequency is the same. Okay, although the frequency is the same. Be very careful with this. Okay, that's refraction. Okay, number 16. Number 16, when you see Young's double slit experiment or any interference experiment, there's only one formula involved. This is a calculation question, and the answer is lambda equals to AX over D. Okay, let me show you the experimental setup for this now. Whether it is whether it is water lah or light lah or sound, the experimental setup is always the same. So if you have from the double slit, okay, this is a double slit, okay, and then this is a screen. Okay, now the distance from the double slit to the screen is the letter D. Okay, the distance between the slits, this distance is A. Okay, the distance between the slits is A. Okay, the problem now is the X. Okay, so on the screen, you will get something like this. You will get light, dark, light, dark, light, that you get alternating. If it is sound, you will get soft, loud, soft, loud, soft, loud. You always get an alternating pattern and it's pretty much the same distance. If it is water waves, okay lah, fine. If it is water waves, you get strong waves, strong, weak, strong, weak, strong, weak. That's what you will get. Okay, but either way, X, okay, this is probably the most difficult. X is the distance between two successive. Again, the word successive. Successive means they are next to each other. Okay, two successive bright or two successive dark or two successive loud sounds or two successive soft sounds. They must be successive. So the problem now is the distance between the double slit and the screen is 1 meter. So this is D, no problem. The wavelength is given. Wavelength is lambda. Okay, what is the distance between the two slits? They want you to find A. The problem is what is the X? Okay, and generally when students look at this, the only thing they see is the number only. They don't see what the number represents. So the first thing they will do is, oh, okay, lambda. So 5 times 10 to the power negative 7 equals to A times 0 0.05 over 1. Right? If only life was that easy. You just substitute everything in only. Okay, and that's why the definition, okay, the definition for the X is very important. X is the distance between two successive. How many successive do you see in this 0.5? 1, 2, 3, 4, 5. There are 5 successives. There are 5 pairs in this 0.05. So one pair is how much? 0.05 divided by 5 lah kan? Okay, so X is actually 0.05. 0, 1. 0.05 divide by 5. Okay, very common paper 1 question. We see this all the time. Okay, and we always see people falling for the wrong answer lah. You know, the wrong answer which you can calculate will also appear inside the answer, inside the 4 choices. So you need to make sure that you understand this formula very correctly. Lambda equals to ax over d. The x is the most important. It must be 2 successive. So we're talking about 5 times 10 to the power of negative 7 equals to a times 0.01 over 1. Okay, so I think the answer is A. Is the answer A? Sorry. Yeah, the answer should be A, I think. 507 divided by 0.01. Okay, the answer will be A. Yeah, somebody said yes. Okay. Sorry, thank you. Okay, so the answer will be 0. So be careful about this one. The formula is pretty easy. Okay, the formula is pretty easy. You just have to remember what all these long letters, what all these words mean, or these letters mean. But the X is the one that I'm always very worried about. And this is very common. Okay, tengok berapa pasang yang ada, divide by the number of pasang. Okay, don't be tricked into this. All right, question 17 is light, so I'm going to move on to paper 2 because I know that the rest of the questions will not have waves anymore. Once they move on to the next chapter, they will not revisit the next chapter. It's very cruel kan. Kejam. Kalau sekejap form 4, sekejap form 5, sekejap chapter 1, sekejap chapter 6, no lah, they won't do that. Okay, examiners are very kind one. Kind. Okay, they're very kind. Okay, paper 2, this is not. This is light. Okay, you see this is light, you know. This is definitely not waves. Okay, it's electricity. This one I've marked here from 4, from 5, chapter 6, so that you don't have to study this for trials yet because we haven't learned. At least for the students that I'm teaching, we haven't learned. This is force and motion. Wow, do we not have any wave questions? I'm sure we do. This is electronics. Sorry, electronics. Oh gosh, senior moments. This is gravitation. We can skip this. This is specific heat capacity, so it's heat. Okay, so we can skip this. Oh, that means it's essay question. Okay, Barton's pendulum. Okay, Barton's pendulum. This Barton's pendulum is the only time it appears is in 5.2, which is damping and resonance. Okay, and this Barton's pendulum shows exactly what resonance is. Okay, so the idea behind Barton's pendulum is when you move X, only the one that has the same length as X, okay, this will oscillate, okay, with maximum amplitude. Okay, alias resonance. Okay, with X. Okay, so you have 5 different pendulums, A, B, C, D, E, and then you only move X. Okay, the common misconception that a lot of students get is, oh, A, B, C, dan E langsung tidak bergerak, which doesn't make sense at all, really. If you tie everything to a string, you mean A, B, C, and E will try very hard not to move and will just stay still. No, cannot. I'm sure they will move. They will definitely move. Okay, but there is one that will move with the maximum amplitude, and it is the one that has the same length of string as the X, as the driver pendulum. Okay, everybody else, A, B, C, and E, will oscillate. It's just not going to oscillate very much. Dia memang sikit-sikit sajalah. But D, because it is resonating with X, okay, dia I tell my Form 4 students resonance is something that all Gen Z people will surely understand, because it is the concept of stand and +1 comes with the word resonance. Before words like stand and +1 came up, us Gen X us Gen X and boomers have already come up with the word for it, and the word is resonance. Okay, I resonate with what you are feeling. Okay, I resonate with what you're saying. No, it moves my heart, dear. Menjadikan saya excited. Okay, so don't think that your stand and your +1 is so special. Okay, people have been using it for centuries. Okay, it's just that they come up with a short form which is called +1. Wow, and they think that it's so hebat. Padahal the word is actually resonance. Okay, when you are vibrating together with somebody else, when you resonate with somebody, you agree with somebody, that's what resonance is. Okay, you will oscillate with the maximum amplitude. The guy is moving with an amplitude of 0.1 meters, you are also moving at 0.1 meters because you have the same. Okay, so the reason for resonance has to do with the natural frequency. Okay, so resonance occurs when something that is not moving, okay, when something that is not moving is forced to oscillate at its natural frequency. Okay, the definition is like what? Balik lah. Okay, but that's what it is lah. Okay, contohnya lah, let's say okay, and I'm just saying this across the board, and this is not meant to mengecam sesiapa lah. Let's say you are an let's say lah, you are an anti-vaxxer lah. Okay, and you find somebody that is talking about anti-vaccine and everything, right? You will surely resonate with that one. No, you will surely, okay, saya setuju dengan apa yang kamu buat, because your natural opinion is saya tidak mau kena vaksin. I'm an anti-vaxxer. Example. Okay, if you're an anti-vaxxer, fine, you are entitled to believe what you want, but you also have to bear the consequences. But that's basically it. Okay, when somebody is moving, when this X is moving, the only person that has the same frequency as X is D, because the length of the string is the same. So D yang pada asalnya tidak bergerak, dia akan terpaksa mengayun. It will be forced to oscillate at the same natural frequency as X. And when it oscillates, it will oscillate with the maximum amplitude. Okay, so what is the meaning of frequency? Frequency is the number of complete oscillations in 1 second. I mentioned this in the previous question. Okay, explain how the phenomena of resonance occurs. Okay, so what I mentioned just now, all in blue, is the very long and grandmother story lah. Okay, but basically, if you want this one, hold on now, let me see if I can find a nicer answer. Okay, so your first point, okay, your first point will be this lah. Okay, pendulum D and X, okay, have the same length. This is the single most important thing. You need to mention the one that has the same length first. Okay. Second point. Both D and X have the same frequencies. Okay, both D and X have the same frequencies. And then only you talk about the swinging lah. Okay, so when X is displaced, all pendulums start, and I got no more space already. Sorry. I can't go. Okay, start to oscillate. Okay. Sorry, hold on. Okay, sorry. Start to oscillate. Okay. And then your final point is, since D has the same frequency, okay, it will resonate and oscillate with maximum amplitude. Okay, 4 marks, 4 points. You can write more than 4 sentences if you want. Okay, actually, the actual explanation to this is about 6-7 sentences, but I'm just compressing it down to 4. What I'm looking for, okay, what I'm looking for is First point, I'm looking for the fact that they have the same length. Because itu yang menjadi kamu punya sebab kenapa mereka ada the same frequency. Okay, that's the second point. Third point, when you move X, all the pendulums will start to oscillate. Okay, but only one will oscillate with maximum amplitude. Okay, that is the D, that is the pendulum D. Okay, pendulum D, because it is the same length. Okay, yeah, take screenshots, people, because I need to I kind of want to cover at least the first model paper. All right. Okay, let's go to this one. Okay, the 10-mark question. Okay, so the 10-mark question says, study the specifications of all 4 radar systems, explain the suitability, determine the most suitable radar system to be used in the position of an aeroplane. Now, if you're my student, you will know that I am insisting, I insist and I'm forcing you to write your answer for this in table form. Okay, I don't know about teacher He's class. She may or may not do this, but for my students, if you don't write your answer in your 10-mark question in the table form, I will give you an immediate 0. I'm not even going to bother marking. Okay, be warned about this. I have already mentioned this. I'm not going to say it again. Okay, now how do you approach questions such as this? What you need to do is you need to analyze the table first. Don't jump into answering it. Okay, unless you're very pro and you know what to do, don't jump into it. Okay, analyze the table first to see which one you want. Okay, now the diameter of the parabolic dish, okay, you have 4 choices like 10, 3, 9, or 5. Okay, and if you remember, I've always mentioned now that whenever the choice given to you is a number, don't write the number. You either write higher or lower. Okay, higher or bigger. Okay, lower or smaller. Okay, so for a parabolic dish, okay, we are using this for aeroplane for this. Yeah, okay, radar in an airport. Okay, we definitely want a large diameter. Okay, we want a higher diameter of parabolic dish. Okay, so we are looking at either 10 or 9. You cannot write 10 or 9. You just write bigger diameter or larger diameter of this one. Okay, and the reason for this, I'm going to write the reason in red. Okay, usually big diameter. Okay, usually big diameter parabolic dish is receive more signal, which makes sense lah kan. If your dish is very small, kan, kalau kamu punya mangkuk sangat kecil bahkan kamu tidak mampu minum banyak sup bah. But if your bowl is very big, then you can store a lot more soup inside lah. Just like the parabolic dish now. If you have a parabolic dish that's very big, then you can receive more signals and you will get a clearer transmission. But if you're very kedekut and you have this tiny dish, don't expect to have more signals. Pasal dia ada tempat mau pergi. Kan? That's why if you have ever been to Kopungit, okay, Bukit Kopungit, there's this the airplane control, the satellite dish, right? That's pusing. It is like this shape, It's like a sort of like a square shape. It's huge, it's this huge structure, which is like, I think it's like the size of a lorry, okay, of a standard lorry. It's very huge, very wide, okay, in order to receive more signals, especially in times where there are many planes coming in, you need to be able to receive all the signals. So big diameter of the parabola, okay. Secondly, the type of wave is either radio wave or microwave. Okay, this one you need a little bit of know-how, but this one we will choose microwave. Okay, why would we choose microwave? Because, okay, in terms of waves, if you're asked to choose between radio wave, microwave, infrared, ultraviolet, yada, you talk in terms of frequency or in terms of wavelength. Okay, so you will talk about in microwave, okay, microwave has a high frequency. Okay, and when we talk about high frequency waves, we are also talking about high energy wave. This is also another acceptable answer. Okay, microwaves are generally high in frequency, higher than radio waves. Okay, and definitely much higher energy. Okay, very important. Radio waves not so good lah, and especially because radio waves are more for even longer distance communication. Radio waves are different in a sense where we use radio waves for because it has a bigger wavelength. Radio waves, yeah, it's a bigger wavelength, able to travel far. We want it to travel far. But for kegunaan airplane, right, it's not like the airplane is in KL and then you want the parabolic disk in KK to receive the signal. For what? No need. Okay, it is near, but not as near like like saya dengan ini kipas lah. We're not talking about that near. Okay, so radio waves is a bit too far. Radio wave is, the radio station is in KL and you're listening to the radio station in KK. So you need a very long wavelength. That's why we use radio wave. But microwave, the airplane is just like about 100 kilometers away only. So we don't need such a big wavelength. What we need is a big frequency. So big frequency means big energy. Big energy means we are able to get a clearer signal. That's what we want. Okay? And we are able to get it faster. That's also very important to us. So we use microwaves for that. Okay. All right, the distance from the parabolic dish, the signal receiver from the parabolic dish. Now, this is a common question, and whenever people see this, they are like, what? Okay, they don't really understand what's going on. So when we talk about the distance from the signal receiver and the parabolic dish, we're talking about, okay, let's say, how do I explain this now? The satellite dish, okay, satellite dish. This is my sad attempt at the satellite dish. So satellite dish, okay, satellite dish like this. Okay, then the tapak and so okay. So the satellite dish has this receiver that is over here. Okay, there is a receiver that is over here lah. So what happens to the waves is that when the waves come over here, they're going to kena pantul ba. Apa ini? Sorry. Okay. When the waves come and hit the dish, it's going to be reflected. And when it reflects, it needs to reflect onto the receiver. Okay, because waves can come from anywhere. Okay, like this. So come from here and then go here, come from here and go here. Of course, there is waves that's going to directly touch the receiver. I'm not saying that there is none. Okay, of course, there are waves that directly touch the receiver. But what about the waves that are being reflected? Okay, so if you remember reflection, you know that all reflection is focused on the focal length. Right? When you have a mirror, okay, when you have a mirror and this is the focal length, when the light waves come, okay, it's going to pass through the focal length. It must pass through the focal length. So the distance of the signal receiver, which is this thing up here, has to be ngam at the focal length of the parabolic dish. Okay, and why do we do that? Because so that it is able to receive more signal. Yeah, can lah. Okay, so the reason for this will be signal will be focused on the receiver. Okay, semua isyarat bahkan akan tertumpu pada the receiver. So you don't have all these isyarat yang lari pergi sini sana lah. We don't want now. We want all of it to be focused on the receiver so that we don't have to, hello, what do you say? Can you please repeat what you said just now? Over. repeat everything again. We don't want that lah. Because plane is about to land and then you're still asking the pilot, sorry, Captain, what do you say just now? Can you please repeat again? We don't want that to happen. Okay, that will be a disaster in the making. So because of that, we want the distance of the signal receiver to be ngam at the focus. Okay. Lastly, and this is probably the most logical, how high do you want your parabolic dish to be? Obviously, you want it to be at a high position. Okay, because at a high position, you have less obstruction. Yeah. Okay, less obstacle. Kurang halangan lah. Okay, less obstacle is what we're looking at. Less, there's nothing to block the signal lah. Okay, if you put the parabolic dish right next to the airport, okay, it's going to be a disaster. Okay, because everything is going to come towards the receiver, so we don't want that. Okay, all the planes are going to start blocking. So because we're not using radio waves, we're using microwaves. We need to be very careful of that. Okay, radio waves are, don't have to be so high, so not so bad, but higher is better. Okay, but definitely microwaves, you need it to be as high as possible. That's why you always see the satellite dishes are on top of the hill. The best example we have over here in KK is the one in Bukit Kopungit. Okay, I can send you the photo. Every time I go to Bukit Kopungit, I always see that one and I'm always reminded of this question. Now, when you analyze the table, you will find that only R matters. Okay, R is the only one that fits all this. Okay, so I'm not going to revise with you how to answer this question, but I want you to take note, especially the two classes that I teach, the 10th mark. Okay, the 10th mark also equals to the magic number 440. You know why lah? Okay, you know why I say 440. Okay, you want to avoid that 440 for your exam this time. Okay, if that question is in waves, then we are done. Okay, I think maybe to end today, I'm just going to go through the paper 1 questions in the second paper, and then we will call it a day. Okay, so same thing lah. The first few questions definitely not waves because you know that it's not from that chapter. Let's look for the heat question. Okay, this is the heat question. After heat is wave. Okay, this is still heat. Then here we are, waves. Okay, which of the following diagrams is correct to show a transverse wave, amplitude of 4 and wavelength of 8? Amplitude is the highest from the equilibrium position and maximum displacement from the equilibrium position. Oh, sorry. Okay, MDFEP. So, amplitude of 4, this will be correct, this will be correct, this is definitely wrong, and this one lagi lah salah. Okay, so the C and D are out. Okay, wavelength. Wavelength is distance between two troughs or two crests. Okay, this is trough, so this is the answer. Why is this wrong? Because it's not even one complete oscillation. It's just half an oscillation. Okay, so tak boleh. All right, so the answer for this will be A. Remember the definition for amplitude and wavelength. Okay, very important for this topic. Okay, diagram 7a shows an incident wavefront of a plane wave approaching a barrier. Diagram 7b shows reflected. Okay, reflected. So, antara berikut, which of the following statements is true about the incident and reflected waves? Incident wave has the same speed as the reflected wave. True. Okay, in reflection, okay, remember just now when we were talking about refraction, I said refraction, only the frequency is the same. Everything else is changed. Velocity change, wavelength, sorry, velocity change, wavelength change, direction change. Okay, so everything changed. Only the frequency remains the same. But in reflection, okay, everything is the same except the direction. Hold on now, I feel that there's something wrong with what I'm saying, but I just need to, sorry, senior moment. Kenapa saya ragu-ragu ini? Yang part saya cakap pasal refraction lah, kejap. Yeah. Gosh, I don't. Okay, sorry. Refraction, correct. Only the frequency doesn't change. Everything else changes. Okay, but in reflection, everything doesn't change. Only the direction change. Okay, so the incident wave has the same speed. Correct. Okay, the incident wave has a longer wavelength. Is definitely wrong. The wavelength doesn't change. You just change direction only. Incident wave has the same frequency. Is correct. So the answer is 1 and 3 only. Okay. I probably want to talk about this a little bit. Do you know what kind of questions these are? There's a difference. A question where the answers are A, B, C, D. This is called a multiple choice question. Soalan aneka pilihan. Okay, multiple choice question. This kind of question where there is a 1, 2, 3, and then you have to figure out the combination for the answer. This is called a multiple combine. Sorry, combine. Yeah. Multiple combined choice question. Okay, soalan aneka gabungan. First, you have to decide 1, 2, 3, which one is the answer, and then after that, you have to combine the answers together. Okay, in the paper 1, multiple choice questions will be antara 30, sorry, antara 36 to 39 questions will be multiple choice. And the multiple combined choice is between 1 to 4 questions. Okay, minimum 1 question like this, maximum 4 questions will be like this. So there is more questions than just A, B, C, D lah, 36 to 39. So if there is 37 MCQ, there will be 3 MCCQ. Begitu. If there is 39 MCQ, there will be 1 MCCQ. Definitely at least 1 MCCQ like this. Okay, so take note of this lah. I think in your trials, I can't remember. Macam there are 4 lah. 4 or 3 lah. Okay, MCCQ questions. Okay, so just take note of this lah. All right. Interference. Do we have time? Okay, just a little bit more lah. Let me finish this one and number 16. Okay, until number 16. Last two. Okay, then we'll call it. Now, interference. When interference happens, there's 2 types of interference. There's constructive and destructive. T. Okay, constructive is when crest plus crest. Okay, or trough plus trough. Destructive is when the crest plus the trough, okay, combines. Okay, when one wave punya crest and another wave punya crest, when they combine, constructive, it becomes bigger. One wave punya trough and another wave punya trough combine, constructive. Destructive is one wave is like this and then the other wave is coming down, one crest, one trough, sorry, one crest, one trough combined, 0. Okay, it will destroy itself. Okay, constructive interference happens at the antinode lines and destructive happens at the nodal lines. Okay, node lines. So we need to know what these points are called. Antinode points, node points. Okay, titik antinode lah. Why do they like to make our lives difficult? Why can't we just call these points constructive interference points? Well, you can't ask me. I'm not the father of physics. Okay, but our great ancestors of physics have said, okay, let's call this constructive interference points antinodes. Okay, and then let's call this destructive interference as, if one is antinode, let's call this nodes. Okay, so you have to ask the fathers of physics now, why do you call it antinode? The word anti means, destroy. I don't know. Okay, interference, destructive interference happens when it is one crest, one trough, one fixed line combined together with one dotted line, which is what we want to look at. Okay, and so point A cannot because it is crest and crest. Point C is also crest and crest. Point B is the answer because this is a crest and this is a trough. Okay, D is trough and trough. The dotted lines are trough and the straight lines are crests. Okay, so you need to, destructive means one dotted line and one straight line combined together. And the only place where this happens is at point B. Okay, all right, last question. What is the type of wave used in a remote control? This one a lot of people get wrong, but actually the answer is infrared. It's a fact. Okay, remote control for your car, for your TV, your titit, okay, all this, anything at titit that requires a near distance. Near, I'm saying near, but it's very relative lah. Okay, so like now I'm here and my TV is about, say about 4 meters away. Okay, can I turn on my TV using the remote control? Can, if if I'm directly in front of the TV lah, at 4 meters can, because the infrared range is is not very wide lah. You definitely, a lot of people think that remote controller, the car use microwave. Walao. Microwave means what? Microwave means I'm on the, let's say my house is on the 4th floor. My house on the 4th floor, I can open my car door from the 4th floor. Okay, that's the use of microwave, cannot. It's very dangerous. Okay, what if you're staying on the 20th floor of your house, and then you accidentally press the unlock button in your car, and then because your car used microwave, you accidentally unlock your car, and then somebody come and steal your car. Okay, no. We use infrared because we want near distance. But that, and this question has come up before, trial question on SPM. They say they want you to modify the remote control for some reason or another, modify the remote control so that it can receive waves from a further distance. Okay, then this is where you use microwave. Okay? Infrared is too near. Before Bluetooth came out, okay, I'm going to end with this. Okay, before Bluetooth came out, do you know how we used to transfer data from one phone to another? We use infrared. Okay, we use infrared. We call this IR receivers. This technology is so beyond you. Okay, nobody uses this nowadays. But last time the phones, we didn't have Bluetooth. And if we wanted to share contact, okay, and we are so lazy to type out the number inside this one, right? Okay, when I share contact, you know what you do? You take one phone, and then we look for the IR, we look for the infrared signal place. There's a hole somewhere, okay, that says infrared. And then we look for the other phone, and we look for the other one, right? Then we make sure that it's together like this. Seriously. Okay, we need to make sure that the two IR sensors touch. And then after that, we cannot touch, we cannot move, because the moment you move it a little bit, that's it. Habis, whatever data you're transferring is gone. Okay, it needs to be touching and it cannot be moved at all. So that's why when in last time sangat biasa kita nampak kan orang letak dua telefon di atas meja kan berbentuk huruf L lah, dia punya punggung ke punggung lah. Very strange. Nowadays if you see it's very strange looking lah. Okay, but in those days before Bluetooth lah, AirDrop lah, apa itu share kan pakai lisan, we used to use IR, and it's so frustrating because all you want to do is just share the contact. Kau mau pindah nombor telefon saja, and one telephone number is like maybe a few kilobytes lah, two or 3 kilobytes of data. Okay, itu pun akan mengambil 5 minit. It will take 5 minutes to transfer. I know, to transfer 2 kilobytes, kilobytes, not even gig, 2 kilobytes of data just to transfer using IR. And you have to make sure that the connection is secure, and then nobody touch the table, nobody shake the table or anything, because the moment the table shake, that's it, the connection is lost. Okay, how far have we come today? Okay, saya boleh hantar je apa-apa dengan kamu melalui cloud. Okay, now we can just totally transfer information to one another. You probably got, those of you who are not in my class, you probably got this module from somebody's cloud. Okay, how far has information transfer come since then? Okay, but definitely IR, infrared masih lagi ada kegunaan hari ini lah. We use it in remote controls. We use it in, if your house has a automatic gate, we use IR. Kan? You have to come near to the gate, then only you open the gate kan. You don't from Bataras, lepas tu kau tekan kau punya gate from 2 kilometers away, you tekan the house gate, you expect the gate to be open. No lah. Okay, it has to be a near enough distance. So ada kalanya there is still some use lah, masih ada kegunaan untuk near range communication. Okay, things like car alarm, things like remote control TV, all these are near range, masih ada guna. But definitely not for phones nowadays lah. Okay, kalau phones more near range, susah lah. All right, everyone, we'll continue with paper 2, waves, and then after that, light, with the paper 1 tomorrow. Is it tomorrow? Tomorrow, then? Yeah. Okay. Right. Hi, everyone. Let's continue with our physics component. So yesterday, we answered this question. I totally forgot. I totally skipped the calculation question, which is, I don't know why I was in such a hurry to finish the other question. So I'm going to come back to this question. I'm going to talk about this calculation question, because it's not that difficult. Okay, it's quite simple, but let's do it. Okay, so ultrasonic waves are transmitted from a ship to seabed to determine yada yada. You're given the frequency is 25 kilohertz. Okay, it travels at the speed of 1,500 meters per second, and then the time is this one lah. Okay, the time. Sorry, it receives the echoes of the ultrasonic waves after the waves are transmitted. Okay, so if you imagine the situation, this is the ship. Okay, this is the sea, and this is the seabed. So it's going to send these waves out, and then the waves are going to return back. Okay, so the time taken for it to go back and forth is 0.12 seconds. Okay, the time taken for it to go back and forth one time. Okay, so what we want to know is what is the height? Okay, what is the height or the depth of the sea? And this one is a very standard formula. It is not given in your formula list. You have to know this. Okay, so the formula is D equals to VT over 2. Okay, V is the speed, T is the time in seconds. Okay, so this will give you 1,500 times 0.12 over 2. Okay, and this will give you 90. Okay, 90 meters below sea level, which is pretty deep if you think about it. 90 meters, very deep. Yeah, 90 meters is very deep. Okay, boleh pecah kau punya gegenap telinga itu kalau kau masuk. I don't think we can survive more than 10 or 12 meters under the sea without proper equipment. Okay, then we have to count the wavelength. Okay, and this is where the frequency comes in. If you notice that in this first question, we didn't even use the frequency at all. Okay, and then and because we are using it for this one, okay, how do we count the wavelength? We have to use the equation, the wave equation, which is V equals to F lambda. Okay, I think one of the biggest things that a lot of physics students have to get over is the fact that sometimes the thing that they want to find is not necessarily a lot of people will say what? No, the wavelength okay, lambda equals to what's the formula? No, you shouldn't be doing that. Okay, you should know the formula and know how to manipulate the formula to find what you want. Do you have the wave speed? You do, 1,500. Do you have the frequency? You do, 25,000. Okay, I change kilo to to biasa lah. Can I count the wavelength from here? Of course you can. Okay, if you can't, gosh, 25,000. Okay, so the lambda will be 0.06 meters. Okay, of course, getting the unit is also another matter. You need to make sure that you get it correct. Okay, so but the good thing is when you talk about waves, okay, bila kita bercakap pasal ombak, gelombang, okay, usually these are the only two formulas that are very important. Of course, the other important formula is the one that we discussed yesterday, which is Young's formula, the interference. Sorry, I'm going to go straight to this. We discussed this yesterday, right? The interference formula. Oh no, sorry, that's the other question. Okay, so Young's formula is lambda equals to AX over D. But this one only use this for interference. Okay, the other two formulas, V equals to F lambda and D equals to VT over 2. Okay, these two are very more commonly used, okay, compared to the interference formula. Okay, this by far, okay, this is what we call the wave equation. Okay, it is the most commonly used formula in this chapter. Okay, yang ini, this is for interference. Okay, and this one is only one situation, depth of sea. Depth of sea, or okay, or another one is distance from the airplane to the satellite dish. That one also is the same situation. Okay, so this D, not necessarily the depth of the sea. It can also be the distance from the airplane to the satellite dish, because airplane sends a signal to the satellite dish hantar balik signal. So the time where they hantar balik the signal is this T over here. Okay, so we use in these situations, okay, distance two objects. Okay, distance between two objects, we can also use this particular form. As long as you know what is the wave speed, okay, or as long as you know what is the time taken for the signal to return back to itself. Okay, but now what I want to do is I want to go into this second model paper to look at the to look at the wave question if there is. Okay, question 1 don't have. Question 2 is transistor. Question 3, this is Form 5, Chapter 7. Question 4 is gravitation. Question 5, okay, this one. So diagrams show the pulses displayed on a cathode ray oscilloscope when a girl places a tambourine in front of a brick wall and a concrete wall. Okay, so you have these two situations over there. Okay, so the girl is playing a tambourine while on a brick wall and then against the concrete wall. And so you look at this oscilloscope reading and this oscilloscope reading. Okay, you find that the amplitudes are very different. Okay, look at this amplitude and look at this amplitude. Okay, because I'm very sure that the next question is a compare question. Ta-da! Okay, first of all, sound wave. We've learned this yesterday. Sound wave is a longitudinal wave. Okay, I went into a very long discussion yesterday about what is a longitudinal, what's transverse, what's the difference. Please remember this. But the example of the longitudinal is only one at your level now, okay, which is just sound wave. Now compare the characteristic of the surface of the reflectors. Okay, so this is something that is a little bit, we call this a little bit rare. Okay, usually when we compare, we say this is bigger than the other one. This is smaller than the other one. But now we have to compare the characteristic. Okay, so when we compare characteristic, we cannot say this is bigger or this is smaller because the characteristic is different. Okay, so if you have to compare the characteristic, okay, maybe you can say, okay, 5.1 is a brick wall, 5.2 is a concrete wall. So you can say that 5.1 is uneven. Okay, 5.2 is more even if you want. Okay, or more smooth. Okay, or smooth. Okay, characteristics. Don't say, okay, please don't say this. 5.1 is a brick wall and 5.2 is a concrete wall. Okay, it's like, duh, you can see it, it's already written there, no lah. Okay, compare the characteristics. So you have to talk about what is the difference between a brick wall and a concrete wall. Okay, concrete wall is usually, more smooth, like the wall here, very smooth. Okay, brick wall, you have all this lekuk, so it makes it very tidak licin lah. Okay, so you can say that 5.1 is uneven or not smooth, 5.2 is more even or is more smooth. Okay, we would say that kind of comparison. So be a little bit careful about this kind of comparison. Okay, I know that especially for the classes that I teach, when I train you for compare, you're always looking for bigger, smaller, bigger, smaller. Okay, I know, but this is just one of those questions where, it is a little bit different. And it's good that we are exposed to this kind of questions so that we know that, okay, sometimes we have to be careful, okay, because not everything is bigger and smaller. Most of the time, yes, it is bigger and smaller. Sometimes you get all these weird questions, so be aware of it. Okay, amplitude of the reflected sound waves. Okay, this is where you know already lah. Okay, the amplitude, obviously 5.2 is bigger than 5.1. Okay, now, again, if you are my student, okay, I will say this again and again. Comparing questions, I insist that you write the answer in full. Okay, I will not accept this kind of answer. Okay, 5.1 is less than 5.2. Okay, although we know the amplitude definitely 5.1, so I want you to write a full sentence. Okay, the amplitude of the reflected sound waves in diagram 5.1 is smaller than the amplitude of the reflected sound waves in diagram 5.2. Okay, I want it this way. My student lah, okay, those of you under teacher he, you follow what teacher he says. But if you are my student, SA and ST, yeah, fine. If you're my student, okay, I insist that you write it this way. I will not accept this kind of answer. Do you know why I don't accept this kind of answer? Not just because I'm very fussy, kerana saya cerewet, because I've seen this happen before. Student not sure, student not sure. So he's not sure whether it is equals to or more than. So he write like this, 5.1. You tell me what kind of marks am I supposed to give you this? Okay, sorry, it's not even this, it's not even like this. You know how he write? Let me show you how he write. I've seen this many times, not just one person, okay? I've seen this so many times until I get very fed up already. So people write like this. Because he's not sure whether it's 5.1 more than 5.2 or 5.1 equals to 5.2. So when you write like this, what do you expect me to do? Let's say the answer, the answer is 5.1 is more than 5.2. But you write your answer like this. I've seen this again and again. Okay, trust me. Maybe you're like, saya yakin saya tidak akan buat begitu tu. So tulisan saya bukan macam tu. Okay, anything can happen during the exam. They never leave anything to chance, especially when you're talking about exam. Okay, why would you want to destroy yourself by being so lazy? Okay, he wasn't sure whether it was equal or more than, so he wrote this kind of answer. Immediately I gave him wrong. I said, I'm not giving any marks. Saya tiada istilah apa ragu-ragu lah. No, tiada. If I don't understand your answer, I will immediately give it wrong. Okay, and from then on, I tell my students, don't give me this kind of answer. Because tidak nampak bah. And I also see the student sebenarnya dia mau tulis begini tau. Mungkin dia mau tulis begini, tapi disebabkan exam kan, you write so fast, dia pergi tulis macam ni. Okay, this one, kau tengok. Let me zoom in for you. It's not connected. So how? Okay, I've seen this happen again and again. A+ students and also failing students all fall into this trap because in the exam, your mind is working very fast that sometimes things like this you forget. Okay, and that's why I'm very fussy about this. I say for this kind of question, write in full sentence. Okay, if you don't write in full sentence, my students lah. Okay, you don't write in full sentence, I won't even give you anything. I'll immediately give you a 0. Okay, be warned. Okay. State the relationship between the characteristic of the surface of the reflectors and the amplitude. We find that when it is uneven, okay, the amplitude is smaller. Okay, so you only need to do it one way. Like you don't have to write it both ways. So you can say when the surface of the reflector is uneven, the amplitude of the reflected sound decreases or is smaller. You can also do this if you want. Okay, again, as I said, this kind of relationship is a little bit kita jarang nampak soalan macam ni, tapi ada. There are questions like this. Okay, it's a little bit rare to see because when we talk about relationship, we always have in our mind, oh, okay, the answer is the bigger this, the bigger the that. The smaller the this, the bigger the that. We want that kind of answer. We want to avoid answers like directly proportional, inversely proportional. Let's try not to use those kind of answers. Okay, we use the bigger the bigger. Because, so again, now why I say in paper 2, don't use directly proportional, inversely proportional, because directly proportional, inversely proportional refers to graph. Okay, when we talk about graph, graph say, okay, this is directly proportional. Okay, this is inversely proportional. But here you're comparing situations. You're not talking about graphs. So I don't really recommend giving your answer in terms of directly proportional, inversely proportional. Try not to do that. Okay, the bigger the smaller the bigger the bigger the. Okay, use this. But for this question, it's a little bit special. okay, we talk about the characteristic instead. So we have to write it in a different way. Okay, the amplitude and the energy. Okay, this is where you get this lah. The bigger the amplitude, the bigger the energy. Definitely lah. Okay, the characteristic of the surface of the reflectors and the energy, you kind of have to write the same thing again lah. Okay, when the surface of the reflector is uneven, okay, so uneven, okay, less energy. Yeah, I'm not going to write the whole thing full sentence lah. Okay, I just show you one example and then count it lah. Okay, otherwise I will spend the whole entire hour just writing the answer for this question only. We don't want. Okay, so when the surface is uneven, then the energy of the reflected sound is less, and it's shown by the amplitude. Remember, people, the energy of the wave is dependent on two factors. Number one, the frequency. Okay, the frequency of the wave. Okay, but actually more important than the frequency is the amplitude of the wave. Okay, you can be at a high frequency. Okay, high frequency, okay, which is suara macam ni, okay, which is like high pitch voice lah. But if you're high frequency, but your voice, your amplitude is very low, suara macam ni. Okay, so it's very high but very soft, there's not much energy in there. But if you're high frequency and high amplitude, it is generally accepted that it is high and a high energy. Okay, so just be a little bit careful. Amplitude and frequency both affect the energy of the wave. But when we talk about wave, generally we refer to amplitude first before we talk about frequency. Okay, air traffic controller, yada yada. Name the type of wave that is used in 5.3. I think this should be radio waves, because it cannot be microwave. Wait, hold on now. Microwave. Oh no, what did I say yesterday? Was it microwave or radio wave? I think it's radio wave. No, microwave. Yeah, it's microwave. Sorry, microwave. Okay, microwaves. Because radio wave is for long distance, microwave is for short distance, like this. Okay, this is short distance. Okay, when I say short distance, we're talking about maybe, 50 to 50 lah. Okay, 50 to 100 kilometers. That's short distance. Okay, I think so lah. If I'm not mistaken. Okay, so one of the reasons is, and generally microwave is very easy lah. Okay, low frequency. Okay, low frequency or big wavelength. This is usually the reason why we use microwaves. Oh, okay, that's it. Let's continue. This is light. I don't think we'll see any more structure. Let's just take a look and see if we... This is hydrometer, chapter 2. Question number 9. This is heat. Question number 10 is heat. Okay, don't have. Question number 11 is radioactivity. Okay, so we're done. Let's go into the next chapter, which is light. Okay, light comes after waves. So you kind of know that after this question, the next question is 17 wave. Okay, diagram 12 shows the light ray traveling from glass to air. We find that there is this word critical angle. Okay, critical angle only, when we talk about critical angle, we're talking about total internal reflection. Okay, now total internal reflection happens, okay, when the incident wave is more than the critical angle. Okay, incident wave is the wave that is going from one medium to another medium. It's before refraction happens. Okay, so for example, this is the first condition. The second condition is the light travels from more dense to less dense. This is an important thing. Okay, in order for total internal reflection to happen, it must be traveling, the light must start from a more dense position, for example, inside glass, and wants to go into a less dense, which is air. Okay, like in this case, I want to go from glass into air. So, when that happens, okay, the light will not be allowed to travel into the air. It will be reflected back because the incident angle is more than the critical angle. Okay, ini dua syarat mesti dipenuhi baru dia akan terpantul. Okay, so if the incident angle equals to the critical angle, okay, if the incident angle equals to the critical angle, so the light will travel on the border, which is this case. Okay, if this angle was 44 degrees, okay, the light will travel here, will travel on the border. Okay, but in this case now, our critical angle is 44, but the incident angle is 50. So the incident angle is more than the critical angle. Okay, incident angle is more than the critical angle, condition number one. Condition number two, the light wants to travel from more dense, want to go into less dense. Okay, so once it fulfills these two conditions, D is our answer. It's going to be totally internally reflected. If this condition is not fulfilled, or this condition is not fulfilled, what you're going to get is you're going to get refraction. Okay, which is A and B. A and B is refraction. Okay, refraction is the bending of light waves after it passes through different mediums. Want to go from glass to air. Glass is more dense, okay? Air is less dense. This is very logical. You need to think one. Glass is more dense. Okay, try to knock your head with glass and try to knock your head with air, which is more painful. Of course, the glass is more painful because it's more dense. Okay, there's more. There's more. It has a bigger density. Okay, obviously it's going to be more painful. So, but for total internal reflection to happen, the light must be traveling from the more dense into the less dense. I've seen this before. They switch the thing around. They put up here as glass and here as air. Okay, and then they give this exact same situation. It is a trick question. Okay, if this happens, okay, what you're going to get is you're going to get A. Okay, you're going to get A. If bottom is, less more near. Yeah, okay, you're going to get A. It's going to be refracted nearer towards the normal. Okay, but let's not talk about refraction yet. Let's talk about this one. Okay, critical angle only happens in one subtopic, which is total internal reflection. When you think about total internal reflection, you need to think about the two syarat. Okay, incident angle mesti melebihi critical angle, baru dia akan reflect. Kedua, cahaya itu must be moving from a more dense to a less dense situation. Then, if we combine together with the first condition, then you will be totally internally reflected. However, if the incident angle is the exact same angle as the critical angle, the light will travel at the border. Okay, like this. Anything apart from this is just going to refract. Okay, so our answer for this question will be D. Okay, diagram 13 shows the formation of image by object in the convex lens. Okay, so we're going to assume this is the object and this is the image. What is the focal length of the lens? This is a calculation question. In lens, there's only two possible formulas. 1 over f equals to 1 over u plus 1 over v. And the other one is the magnification. Magnification is v over u or hi over ho. Okay, depending on what is. But the more popular one is this. Okay. Question is, what is u and what is v? That is the common one. U is the object distance. Okay, which is this. V is the image distance. Okay, which is this. This is V lah. Okay. Now the only thing that you need to be careful of when you are answering this question, okay, is that you need to make sure that all these three, okay, the unit is in meter. Oh, it has happened again. Okay, you need to make sure that the unit is in meter. Because, yeah, I know for some strange reason or another, okay, the unit has to be in meter. I also don't know why. So, okay, yeah, wow, I found a faster way to share the screen. Can okay, can see. So the unit for this must be in meter, although they give centimeter. Okay, so we want to find the focal length, which is the F. Oh no, sorry. We want to find the focal length, which is the F. Okay, so we have 1 over F equals to 1 over, how much is this U? If this is 36, this is 30, you know that U is 6. So 1 over 0.06 plus 1 over 0.3. Okay, change it to meters. Okay, what you will get is 20, I think, yeah. So 1 over F equals to 20. Okay, and therefore you get F equals to 0.05 meters, and then only you change it to 5 cm. Okay, take some time to calculate first this. Take some time to calculate this first. Calculate first this, just to make sure that I can get it. The reason why I remember this answer is because the other day somebody asked me, but so that's why I remember. Oh, okay, I think it's 20, but it should be 20 though, correct?
Yes. Correct.
Okay. Okay, so our answer for this will be C. Right, our answer for this will be C. Again, you know what? Let's just experiment now. I cannot remember whether this is the one we have to change. Let's say you change it to, don't change it to centimeter. So 1 over 6 plus 1 over 30 equals to 1 over F. You will get 1 over 6 plus 1 over 30. 1 over F equals to 1 over 5. Oh, okay. But I guess maybe, sorry, maybe you don't have to change it to meters. Why do I say that we have to change it to meters? Can't remember why. Last time when I was taught this, last time when I learned this, I remember I always mentioned that we must change it to meter for some reason or another. I can't remember. What is strange. Okay, now if you don't change it to meter, so it's the same thing. Okay, which pair of lenses can be used to construct a telescope? Two concave lenses with focal lengths of 6 and 9. Concave lenses. Okay, let's talk. Concave lenses is this kind of lens. Convex lenses is this kind of lens. Okay. Now, usually, and I don't remember whether I did this with 4SA last year. Usually, telescope and microscope are the two diagrams. I will say, okay, everyone, you have to draw. You have to learn how to draw these two diagrams. It's very important. Okay. So drawing the diagrams is a very big headache, but it's actually pretty useful. So okay, so the first thing that we need to be very sure is that we are definitely using convex lenses. Okay, so this is out. Ini dua memang out, tak payah fikir sudah. So now we take a look at this. Two convex lenses with focal lengths of 10 and 80. A convex lens with focal length of 6 and a concave. No need. Okay, you would see this is enough. Okay, telescope. Okay, telescope is one of those amazing marvels where this one you have two convex lenses. Okay, where the objective lens, there are two lenses the objective lens and the eye lens. Okay, so this is what we call the objective lens, and this is the eyepiece lens. Okay, objective lens is the lens that faces the object, which is the sun, the star, the moon, the whatever planet you want to see Okay, and then the eyepiece lens is the one that you put your eye in, the one that you put your eye to see Okay, so it's called the eyepiece lens. Now the good thing about the objective lens and the eyepiece lens is that the objective lens has a small focal length, and the eyepiece lens must have a bigger focal length. But even with the small and the big focal length, okay, for telescope, the focal lengths will meet. Here is the FO, here also is the FE. Okay, so the FO is the focal length of objective lens, which is very small. Okay, and the FE is the focal length of eyepiece lens. Okay, And so a perfect picture will be seen where the focal lengths they meet together. Okay, the place where the objective lens punya focal length ends is the place where the eyepiece focal length also is. The same, they share the same focal length. And this is a fundamental difference between the microscope and the telescope. Microscope is the opposite, everything totally opposite. Because, okay, telescope is take something very big and make it smaller so that you can see lah. Okay, for example, you want to see you want to see the sun, you want to see the stars, or so you take the star and then you make it smaller so that you can see. So you take something very big, make it very small. Microscope is the other way around. You take something very small and you want to make it very big. So dia punya fungsi adalah terbalik. And because of that, the function of the lens is also different. Okay, let me just briefly go through microscope. Microscope, the same thing. Okay, you have the objective lens and you have the eyepiece lens. Okay, but the objective lens is very big compared to the eyepiece lens. Okay, so objective lens is very big, the eyepiece lens is very small. Oh, you know what? I'm going to make it even smaller. Okay, eyepiece lens is here. FO is here. Okay, so the focal length of the objective lens is big. The focal length of the eyepiece lens is small. Terbalik from microscope, from telescope. Okay. Secondly, the distance between the two lenses must be, sorry, the distance between two lenses must be more than FO plus FE. Must be more than the two focal lengths combined. They cannot overlap and they cannot ngam touch each other like the telescope. The telescope dia mesti ngam. Okay, the distance between the two lenses is FO plus FE. Memang kang-kang hao. Okay, memang ngam-ngam itu. Dia punya distance between the two lenses must be ngam. But for microscope, because you want to make something small become very big, you need to add the distance between the two lenses. Okay, so the distance between the two lenses must be more than FO plus FE. Okay, in order for this to work. Okay, so these are all the small differences about microscope and telescope that when people do, they always tend to skip lah. But I don't know, I find it it's like, it's because they serve different purposes. Telescope is make something big become smaller. Microscope is make something small become bigger. So you cannot have the same setup now. The only thing that is the same is that both of them use convex lenses. Okay, two convex lenses. We don't use concave lens. We don't use concave lens for this one. So if you look at this question, actually this 6, 9, 10, 80 all got nothing right. It's like very irrelevant. Okay, the most important thing is we need to use two convex lens. Okay, you cannot have one convex, one concave. Ayo, tidak boleh. And definitely not two concave. Okay. All right. Oh, that's it. Let's go to paper 2. Okay, this is force and motion. Oh, this is light. Okay. Diagram shows the student standing in front of a plate mirror. Okay, so this is one. So phenomena cahaya. Sorry. Where's the English version? Oh, the light phenomena that enables the student to see the image of himself is reflection. Okay, so you want to underline this. Yeah, so even in physics now, because this kind of questions, underline the right answer or tick the right answer. Okay, so make sure when you tick correctly. Okay, state one characteristic of the image formed in the plane mirror. Okay, let's talk about characteristics. Characteristics of image, okay, whether it is mirror, whether it is lens, whether it's this kind of mirror also, we have the same standard tree, okay, which is number 1. Is it virtual or is it real? Okay, secondly, is it upright or is it inverted? Okay, adakah dia tegak atau dia terbalik? Inverted is terbalik lah. Tegak means same direction as this one. Okay, and thirdly, is it magnified? Maksudnya the image is bigger than the object, or diminished, means the image is smaller than the object, or same size as the object. Okay, when you talk about the characteristics of the image, you need to have three characteristics. Okay, either virtual or real, either upright or inverted, either diminished, magnified, or same size. Let's talk about virtual and real. Okay, a real image, okay, is an image that can be captured on a screen. Okay, a real image is an image that can be captured on a screen. And this is a little bit hard for us to imagine when we when we are doing all this. Okay, it's a little bit. It's easier when we do lens, because lens, most of the images are real. But for mirror, it's like, I can see the person in there, that's the image, no? So why isn't it real? It's not true. Because you need to remember that mirror, the purpose of the mirror is to reflect the light. Okay, so technically, when the light hits the mirror, it reflects back, right? If I put a screen over here, I should be able to see the reflection on the screen. Okay, and if I cannot see the reflection on the screen, means that the image is virtual. Okay? A real image is an image that can be captured on the screen. Think about the light ray. Okay, if this is the mirror, or if this is the mirror, fine. Sorry, let's say this is the mirror. If I put the light over here, okay, when it bounces back, if I put the screen up here, I should be able to see the picture of the original object, okay, on this screen. Although this is a mirror, I know, although this is a mirror, okay, sebab kau tengok di dalam ada itu. Okay, but even in mirror and in lenses, if you can capture the image on the screen, then it is a real image. Okay, but if you cannot, it is a virtual image. So the image that you see inside the mirror is always and will always be virtual, because your image appears in the mirror, it's virtual. Okay, it will be real only if you can capture it on the screen. So for a plain mirror, there is these three. It will be virtual, it will be upright, and it will be the same size. So you can write this. Okay, virtual, upright, same size. Okay, either one you don't have to write all three Okay, don't be so greedy Write all three for what? Okay, people say one, give one. Don't give all three. Okay, but there is another characteristic about the plane mirror that we need to know. Okay, and this one is very special. Only plane mirror got this characteristic, which is laterally inverted. Okay, dalam bahasa Melayu is songsang sisi. Okay, and those of you in SA, you will know what I'm talking about. I always tell this story one. Okay, when you raise your hand in front of the mirror, if your right hand is raised, you better make sure that the person in the mirror is the left hand that is raised. If you raise your right hand and then suddenly the person in the mirror also raise his right hand, you better move out of the house. There's probably a ghost in the house. Okay, so that's what it means by laterally inverted. Left becomes right, right becomes left. But up is still up and down is still down. That's why it's laterally inverted. Songsang sisi sahaja. Left and right only changes. Up and down doesn't change. Okay? It'd be very sad if you have a mirror that when you look at the mirror, your face is down there and your legs are up. It's even worse. Okay, so it's just laterally inverted. Songsang sisi. Let me just check something now. Hold on. Yeah, that's what I thought. Okay, sorry. My mistake. For telescope, is terbalik. Okay, the objective is big. Okay, and then the eyepiece is small. So actually, this one should be somewhere here. Because I was like, cannot be, or you want to make it bigger? Yeah, sorry. The objective must be the big one. Okay, the objective lens for the microscope or for the telescope, okay, has to be bigger. than the eyepiece lens. Yes. Okay. Whereas for microscope, for microscope is terbalik. Okay. For microscope is the objective is small. Okay. And then the eyepiece is big. Oh no. You know what? I'm gonna rub this off. Okay. So the objective is small and the eyepiece is big. Okay, dia terbalik. My mistake. Sorry. But definitely the distance between the two lenses must be more than the FO plus FE. Okay, that one I know. Whereas for telescope, the distance is num FO plus FE. Okay, it's just that I had confused the distance. Because objective lens, the object is so far away, so you need a big focal length. Yes. Okay, that one I was like, hey, sounds very weird. Okay, sorry for the mistake. Okay, virtual upright same size. All right. So diagram 2.2 shows an object placed in front of a concave mirror. Okay, concave mirror is focusing mirror lah. Okay, so how the image should be formed. First one will be always straight. Oh, sorry. First one will always be straight. And then after that, go back towards F like this. Okay, the second one is from C to C lah. Okay, you just draw one straight line combining this. So when you draw this should be correct. Less than. Yeah. Okay. When you extend this, oh no. Okay, when you extend this to the back, okay, so it's going to meet somewhere here lah. Okay, so it's going to meet somewhere there, and so you will have the image is formed there. Okay, there's only one situation where this happens lah, where the object is less than the focal length. Okay, but the two light rays are always the same. The two light rays are parallel and then bounce back towards F. And then the second one is it will go to C and come back to C. Okay, it will always bounce back towards the C. So when you extend this, you will get this. And then, of course, the question is, give one example of use of concave mirrors in daily life. Okay, so concave mirrors. Concave mirrors. There are many uses of concave mirrors. Okay, you can have cosmetic or makeup. Okay, cosmetic mirror. Concave mirrors, okay, generally concave mirrors are used or in this okay, in this situation is to make the objects look bigger. Okay, to make the objects look bigger, but it makes the field of view, okay, medan penglihatan. Field of view will be smaller. Okay, objects will be bigger. So we use this for cosmetic mirror. We use this for dental mirror. You know the mirror that the dentists use to go and poke inside your mouth to see the all the plaque on your teeth. The mirror makes makes your teeth look bigger so that he can see properly. So it won't be the same size. Okay, the picture of your teeth inside the mirror will be much bigger. So we use a concave mirror for that. Okay, so dental mirror, cosmetic mirror, these are the two most common okay, most common concave mirror uses in daily life. And again, the principle behind the usage of the concave mirrors is this. Kita membesarkan objek, tetapi kita mengecilkan medan penglihatan. The field of view is smaller. Tempat kita mau tengok itu lebih kecil. Kalau convex mirror is terbalik. Okay, if it is convex mirror, okay, for example, the mirror that you see at the side of the road, you can see much more. Or if you go to the 7-Eleven, you go to this one, right? You see the mirror on top of this one. You can virtually see the whole shop one. Okay, and that's what we call a big field of view. Okay, so bigger field of view. Okay, but the size of the objects, okay, the object's size will become much smaller because you want to see more. If you want to see more things, you have to make the objects become smaller. Okay, if you want to see something bigger, concave mirror, okay, if you want to see something bigger, you have to narrow the field of view so that the thing that you want to see is the thing that is focused. So there is a relationship between the size of the object in the mirror and the field of view. Okay, and the different mirrors will give you that different effect. Okay, let's go on to, okay, definitely no more structured questions. Let's see whether there's an essay question. Number 9 is this. Number 10 is this Bernoulli's principle. Number 11 is, what's this? Transformer. Okay, let's go into the second model paper. After waves, right? Okay, interference, IR. Okay, here. Diagram 10 shows a boy try to catch fish in the water. What is the phenomenon that explains this situation? This will be refraction, definitely refraction. What I want you to notice is this question is how to draw this one. So this is the actual fish. Okay, this is the actual fish, but this is what the boy sees. The boy, okay, so how to draw this? Okay, how to draw this? So usually a question, they will give you like this. So this is the boy. Okay, and this is the actual position of the fish. Okay, and let's say, sorry, what a horrendous. So let's say the boy is standing here. Okay, yang paling penting is the cahaya yang masuk di sini lah. Okay, so the shortcut I like to teach the shortcut. What you do is you first draw the fake fish on top of the original fish. Just draw anywhere. Okay, draw the fake fish on top of the on top of the real fish. Okay, so this is the fake fish. This is the real fish. Okay. Secondly, you draw a straight line from the eye of the fake fish to the eye of the person. Okay, just draw a straight line because to us, to humans, light travels in a straight line to us. Okay, our eyes cannot identify. No, our eyes cannot really see the effect of refraction. Okay, itu kelemahan mata manusia lah. Okay, our human eyes can only see light traveling in a straight line. So we cannot imagine that light bends to come towards us. Although in reality, light bends. Okay, so anyway, first step, draw the fake fish first. Anywhere it can be anywhere, but not so near to the surface, just a little bit above the real fish. Then the second step is you draw a straight line from the fake fish to the eye of the human. Okay, the third step is draw the normal line. Okay, where the C and the line meet, you draw a normal line. Okay, and then after that, you finally draw the fake refraction line. Okay, the fake refraction line, this one. Okay, yeah. So technically, what is happening is this fish over here, the light from the fish, as it is leaving the water, it's going to be refracted into the eye of this boy. But since our eyes can only see straight lines, so we are going to imagine that the fish is over here. So this is the fake one. Okay. How to draw this diagram is a very popular SPM question in paper 2. Okay, and the hack this is the hack okay. This is not really how you should draw it, but I find that this hack works Draw the fake fish first, draw a straight line from the eye of the fake fish to the eye of the human. Draw the normal line, and then only draw the refracted line. You work your way backwards. Okay, so anyway, this is refraction. How to draw this one. All right. Which diagram shows the correct reflection of light by a concave mirror? Okay, so you need to take a look at this. The two light rays, okay, they come from any object. If you remember in the question just now, the two light rays it must be parallel and then reflects to the focal point. So we're talking about this one, parallel reflects to the focal point. So this is correct. Okay, why is this wrong? This is going from C. Now, if it is traveling from the center, it can only reflect back to the center. Okay, center to center. Okay, so center cannot be parallel. Parallel to focus, center to center. Okay, parallel to focus, center to center. So that's why C is wrong, because if it passes through the center, it cannot be reflected parallel. This is definitely out loud because it's not hitting anywhere at all. Okay, and this one is also out because if it is parallel, where must it go? It must go towards the focal point. Okay, reflection always happens towards the focal point. If the light is coming from the center, if the light is coming from the object. Okay, center to center, parallel, or to focus. All right. Again, only 2 questions. Why? Why do these people only letak 2 soalan saja? I wonder whether we can finish the structure. Let's try to finish lah, so that Saturday we can do another topic. Okay, wait, hold on. Question 1 is force and motion. Question 2 is transistor. Question 3 is not relevant. Question 4 is gravitation. A lot of gravitation questions. Question 5 is waves. Question 6, electromagnetism, Lenz's law. Question 7. Okay, this will be our last question, I think. Okay, name the type of mirror used. This will be a convex mirror. Okay, convex mirror because wide field of view, smaller object. Okay, the image is smaller. Look at all this. You can see everything inside one mirror. Normal mirror cannot on, right? Okay, so we have a convex mirror lah. Okay, convex mirror is the one that goes in. Okay, well, that's concave. Sorry, coming out is convex. Okay, one reason is this one lah, wide field of view. Hold on, name the type of mirror. Yeah, convex mirror. So it will be a wide field of view. Again, let me just double check. Mana tahu lah kan, saya salah kan. What question is this? 7. Oh no. Yes, okay, wide field of view or wide field of vision lah. Okay, generally when we talk about convex mirror, we're talking about this kind of reasoning. Okay, wide field of view, the objects look smaller. Okay, you want to see more things lah. Okay. Now, reflector, so there's 2 types of this one, the size and the surface condition. In a science fair, you are assigned to design a solar cooker, okay, that can collect sunlight by using a curved reflector. So you have a, you have a reflector, and then it will reflect onto the food. It will reflect the light onto the food, and then the food will cook lah. Okay, so let's talk about the characteristics. Okay, we analyze first. Do we want a convex mirror or do we want a concave mirror? Okay, remember, convex mirror, wide field of view because the light is spread out. Okay, all right. So again, convex mirror, this one is convex mirror, wide field of view. Okay, why is it wide field of view? Because, why is it wide field of view? Because if this is the mirror, the light travels here, it goes out. Light travels here, it goes out. So we see more things. Whereas concave mirror, okay, the light travels here, it focuses. Okay, the light travels here, it focuses on one place. So you see a lot less. Okay, so when you're doing a solar oven, you don't want, you take all the light and then you go and spread the light everywhere else. You want to focus it on the food. Okay, so the answer for this will be definitely the concave. Sorry. Yeah, the concave mirror, correct, the concave mirror. Okay, you want a concave mirror, okay, and the reason is to converge, okay, the light ray, okay, or to focus, okay, the light ray, okay, on the food. The reason for that lah. Okay, we want this. Okay, the size of the reflector. Do you want a small mirror or big mirror? Obviously, you want a big mirror lah. Okay, just like the wave question now, why do we want a big parabolic dish? So that we can get more signal. Same thing with this. We need a big reflector so that we can capture more sunlight. Okay, we can capture more sunlight, we can collect more sunlight. Okay, these are common words now. Okay, collect more sunlight. The more sunlight you can collect and you can focus the sunlight, okay, the faster your food will cook. Okay, yeah, you all did the solar oven project last year, right? So this actually shouldn't be a problem for you. Okay, surface condition. Do we want rough and dull or smooth and shiny? This one is a no-brainer. Okay, this one is science form 1. Okay, definitely we want smooth and shiny. Okay, we want smooth and shiny so that it will be able to reflect better. Okay, better reflection of light. Okay, better reflection of light. So obviously our best choice will be Q lah. Okay, Q will be the best choice. But because this is a structured question, you don't have to write the reasoning again. Okay, take a look at this question. So the type of curved reflector, we just write concave. Okay, the reason, you write to converge or to focus the light ray. Okay, the size is big so that you can collect more sunlight. The surface of the surface condition is smooth and shiny so that you get a better reflection of light. And then the final question is determine the most suitable, and it's only 1 mark. So all you have to write here is the letter Q. Don't need to write the reason. The reason is for the section B question, okay, which you're not, is not, this is section A. Okay, so yes, the same skill, the same skill set. Okay, give you a table, you analyze. Okay, it is the same skill except that structure is a little bit less. Okay, in the essay question, you have to answer a lot more. Okay, you have to give the reason and you know, you need to make sure you get the 10th mark lah. All right, let me just double check one last time. This is this one, heat, and the last question is okay. All right, I think we're done with light. So in the next class, there was a request to do gravitation questions. So on Saturday, we will do gravitation questions, but there are a lot of gravitation questions. So maybe for those of you who are coming on Saturday, who are joining us on Saturday, we may extend it a little bit lah, okay? Because it is our last session. Well, sort of last session lah. I guess if you want another one, you can ask the penganjur of this seminar, okay, to arrange. But this Saturday, we may end a little bit later, so about 10:30, just so that I can finish all the gravitation questions. All right.